Welcome back to Unit 5. In this lecture video, we'll talk about the basics of graphs, and we'll use what we learned to draw the graphs for our 5 class examples of street routing problems. Before we can draw any graphs, we need some vocabulary. Here we have an example of a graph. One thing that a graph has is a set of vertices. Vertices are the dots that you see on the graph, or the specific locations like A, B, C, D, E, and F on this graph. We will also always use capital letters to label our vertices. Edges on a graph are the set of lines that connect the vertices. Notice that they can be straight lines or curved lines. Either way, they connect two vertices together. So to have a graph, we need a set of vertices and edges. The vertex set of a graph is the set of all of the vertices in the graph, and we notate the vertex set for this graph like this. Next, let's define adjacent vertices. Adjacent vertices are any two vertices that are connected by an edge. For example, A and D are adjacent vertices because they're connected by an edge, but A and F are not adjacent vertices because they are not connected by an edge. A loop is an edge that connects a vertex with itself. On this graph, we have a loop at vertex B. The idea of multiple edges occurs when we have more than one edge connecting the same two vertices. In this graph, we have two sets of multiple edges. We have multiple edges connecting vertices C and D, and we have multiple edges connecting E and F. An edge list is a list of all the edges in a graph. For this graph, we have quite a few edges, and our edge list would look something like this. We write capital A, capital B for the edge connecting vertex A to vertex B. We write capital B to denote the loop at edge B. Then we have BC for the edge between B and C, BE for the edge from B to E. Since we have two edges connecting C and D, we'll write CD twice. We also have an edge connecting A and D, E and D, and finally three edges between E and F. Each vertex has a characteristic called the degree. The degree of a vertex is the number of edges that meet at that vertex. For example, vertex A has degree 2 because there are two edges that meet at A. However, vertex E has degree 5 because there are 5 edges that meet at vertex E. An odd vertex is a vertex whose degree is an odd number. An even vertex is a vertex whose degree is an even number. A is an example of an even vertex because it has degree 2, and we notate that as degree of A equals 2. E is an example of an odd vertex because it has degree 5, and we notate that as degree of E equals 5. We can list out the degree for every vertex in the graph, and we can also categorize them as odd and even. If you've survived junior high, then I don't need to tell you what a clique is. But in terms of a graph, a clique is a set of completely interconnected vertices in the graph. Every vertex is connected to every other vertex by an edge. Looking at the graph to the right, if we ignore vertex F and just look at A, B, C, D, and E, we see that every vertex is adjacent to every other vertex. So there we have a clique. However, including vertex F, it's not a clique because F is not connected to every other vertex. It's not even connected to any vertex. A simple graph is a graph without any loops or multiple edges. This graph pictured here would be an example of a simple graph. There are no loops and there are no multiple edges. An isolated vertex is a vertex with no edges connecting that vertex to any other vertex. So necessarily, the degree of an isolated vertex is 0. Now let's take what we've learned about graphs and draw graphs for each of our 5 class examples for street routing problems. Here we have the security guard problem. Remember that the security guard will start and end at his car at the corner of Elm Street and J Street. We will mark every intersection with a vertex, and we will draw an edge for each street connecting two vertices. So drawing a graph for this neighborhood might look something like this. We have each intersection marked with a vertex, and each street denoted with an edge. Now we've taken the neighborhood and we've turned it into a graph. This will make the process of street routing a lot simpler to follow. Make special note of the fact that we did not connect vertices that do not have streets between them. For example, we do not draw edges that cross through the school or cross through the park. Let's go through the same process with the mail carrier problem. Even though the mail carrier walks the same neighborhood as the security guard, we will need to draw a slightly different graph. Remember that the mail carrier will need to walk some streets twice, and we will denote those with multiple edges. Let's once again start by placing a vertex at each intersection. Let's start with the top left corner on First Avenue and draw in the necessary edges. Notice that on First Avenue, there's only homes on one side of the street, so we only need one edge between each of those vertices. Once we get to the park, there aren't any houses on either side of the street, so we don't need to draw any edges around the park. We actually don't even need those vertices, so let's get rid of them. Let's now go down Palm Avenue on the far left side. Again, there's houses on only one side of the street, so we only need one edge connecting these vertices. Going down Arbor Street, there's homes on both sides of the street. So instead of one edge between each pair of vertices, we need two. That shows that the mail carrier needs to walk on both sides of the street, or walk that street twice. The same is true coming down L Street and K Street, with houses on both sides of those streets. Continuing in this way, we can fill in our graph with all edges denoting exactly where this mail carrier needs to walk. Notice that like the park, when we got to the school, we do not need to traverse those portions of the street twice, and we don't need to go around the school. So again, we can actually delete some of those vertices that we don't need. And now we have a graph to represent the mail carrier problem. Let's go on to the UPS driver problem. On the UPS driver problem, if you look closely, there's tiny little X's on each house that needs a package delivered. Since those can be very difficult to see, I've marked each of them here with a red dot. Let's think about where the UPS driver needs to go and does not need to go. They only need to traverse each street one time, and only the streets where there's a home that needs a package delivered. Let's start by marking our vertices that are on street corners near each home that needs a package delivered. Now let's draw our edges only for streets that have a home that needs a package delivered. Now we have a graph to represent the UPS driver problem. Everywhere there's a blue edge, the UPS truck needs to drive to deliver a package. And now we'll go on to problem 4. Recall that with the Konigsberg Bridges puzzle, we have 7 bridges, 2 islands, and 2 sides of the river. We'll label this side up here R for the right side of the river, and down here we'll label this side of the river L for the left side. We'll also label the islands A and D. Each of these pieces of land, whether they're islands or side of the river, will be our vertices, and the bridges will be our edges. Let's recreate this as a graph off to the side. First, we have our 4 vertices, and we'll label them R, A, L, and D. Notice that we have 2 bridges connecting island A with the right side of the river. So on our graph, we will draw that with multiple edges. We need 2 edges between A and R. There's also 2 bridges between island A and the left side of the river. So again, we need 2 edges between A and L. The 5th bridge that connects to island A goes to island D. So we'll draw in a single edge from A to D. The last 2 bridges connect island D to the right side of the river and the left side of the river. So we need an edge from R to D and an edge from L to D. And now we have a graph to represent this scenario. Let's move on to our last problem. With the bridges of Madison County, we have 4 islands, A, B, C, and D. We also have 2 sides of the river, the right side and the left side. These 4 islands and the 2 sides of the river will be represented by vertices. The 11 bridges we will notate with edges. Let's create our own graph off to the side to represent this scenario. We need our 6 vertices, and we'll label them the same as in the picture. Let's start with Island A and draw in the edges to represent the bridges from Island A to other pieces of land. There's a bridge from Island A to the right side of the river, and a bridge from Island A to Island C. Moving on to Island B, there are 3 bridges. Notice that one of the bridges goes to Island D, while 2 of the bridges go to the right side of the river. Going on to Island D, we have already represented the bridge that goes from D to B, but now we need to represent the bridge from Island D to C and from D to the left side of the river. Finally, at Island C, we already have the 2 bridges to Islands A and D respectively. The other 2 bridges go to the left side of the river, so we'll again have multiple edges, 2 edges between C and L. That takes care of 9 of our bridges. Those are the 9 bridges that connect to the 4 islands. There's 2 bridges left, over here and over here. Notice that those 2 bridges go directly from the left side of the river to the right side of the river. So we need to draw in 2 edges between R and L. And now we have our graph to represent the bridges of Madison County. And that will conclude this lecture video. In this lesson, we covered the basic terminology of graphs and used it to draw graphs to represent 5 different street routing problems.